Hi everybody, so this is April. Happy April Fool's Day. This is lecture 28. We're discussing section 8.7 for the second time. We discussed it on Monday, and then you had some problems in recitation on section 8.7, Taylor and Maclaurin series. So this is our second and final meeting on that. So this is a four-part meeting, 6 examples. The good news is the first 5 examples are really easy. So meeting part 1 is using known series to build new series. So there's no new theory today. They're just examples. So example 1. Find the Maclaurin series for f of x equals x cos of 1/2 x squared. Okay, well, we've seen a definition of Maclaurin series. We know how we could do this. We could find each of those coefficients by taking various derivatives of this and then plugging in x equals 0 into those derivatives and building the coefficients. But the idea is we're going to use a known series. So we're going to recall the series for cos x is this. The sum as n goes from 0 to infinity of minus 1 to the n x to the 2n over 2n factorial. Now, how do we get that? Well, we know how we got it. We derived that one. But the idea is for these problems, you're supposed to use a list of known Maclaurin series. So there we go. There's our Maclaurin series for cos x. So those of you who had me for Calc 1, what would you call this? What did I call that kind of thing in Calc 1? Yeah, so more generally, that's just what I called the empty version of the series, or of the function. So then we can use that to build the series for cos of 1/2 x squared. So that's going to be, just take that empty series, minus 1 to the n, parentheses to the 2n over 2n quantity factorial, and just populate it with 1/2 x squared. Now let's simplify that. I'm going to break out the 1/2 to the 2n, and I can clean this up a bit. This should be x squared to the 2n. Break that into 2 terms. The reason is I want to express this as a power series. So coefficients times powers of x. And instead of writing 1/2 to the 2n, I'm going to just put a 2 to the 2n on the bottom. So 2 to the 2n, and then times x to the 4n. So finally, our function f of x, which is x cos 1/2 x squared, is going to be x times all this stuff. So when I multiply all this stuff by x, I can just bring the x in, and that's going to raise that power by 1. So the sum as n goes from 0 to infinity of -1 to the n over 2n factorial 2 to the 2n, that's also down there, and then times x to the 4n plus 1. So there we go. There's our power series. Sorry about the state of the chalkboard. It's very nice that the custodians wash the boards, but it would be great if they washed the boards with clean water. Example 2, under the same heading. Find the Maclaurin series for f of x equals sine squared x. All right, well, so again, we could build this by finding the coefficients. It would involve finding derivatives of this at x equals 0 and building the coefficients. But the idea is to use known power series. Now, in this one, I'm going to display my problem in a different way. In this problem, I had 1, 2, 3, 4 equations. In this new problem, I'm just going to have one equation. So f of x equals sine squared x. Okay, well, from trig, we know that this is 1/2 of 1 minus cos of 2x. And then we're going to use a known series. I'm going to leave the 1/2 times 1 minus. And then in these parentheses here, or this in this bracket, I'm going to put the series for cos 2x. So that means I have to go get my empty version of cos parentheses and populate it with 2x. So the sum as n goes from 0 to infinity of -1 to the n over 2n factorial times 2x to the 2n. All right, well, let's clean this up. This is 1/2 times the quantity 1 minus the sum as n goes from 0 to infinity of -1 to the n over 2n quantity factorial. And when I break that apart, I'm going to have 2 to the 2n on top, and then I'm going to have x to the 2n. Now, we can actually simplify this. What is the 0th term in this series? Raise your hand if you can tell me when n equals 0, what is the term? Yeah. Can you tell me why?
All the exponents will make 1 on top of the 0 factorial as well.
Yeah, so you're going to have -1 to the 0, that's 1. We're going to have 2 to the 0, that's 1. We're going to have x to the 0, that's 1. We're going to have 0 factorial, that's 1. So this is the number 1 when n is equal to 0. So I'm going to break that term off. So this is going to be 1 plus the series starting at 1. So minus 1 to the n times 2 to the 2n, x to the 2n over 2n quantity factorial. So 1 minus all that stuff, okay, well the 1s are going to get together and have a 1 party, so they're going to cancel, and then I'm going to end up with a minus sign. Minus 1/2 times the sum as n goes from 1 to infinity of minus 1 to the n, 2 to the 2n, x to the 2n over 2n factorial. Now let's bring in the 1/2. So I have 2 to the 2n on top. I have 2 to the 1 on bottom. So that's going to kill one of those powers of 2. So I'm going to have 2 to the 2n minus 1. The 2n factorial on bottom is not going to be changed. The x to the 2n is not going to change. What about this? How is that going to change? Well, notice I have a minus 1 times minus 1 to the n. So I have an extra power of minus 1. So now I have minus 1 to the n plus 1. And then starting with n equals 1 and going to infinity. And there we go. There's our power series representation for that. Now, we should think about radii of convergence. For what x's is this equation here true? Did somebody say something? Well, let's look at our table. When you build the Maclaurin series for cos x, it turns out its radius of convergence is infinity. In other words, it's true for all x. So this is true for all x. That is, the radius of convergence is infinite. Same thing over here. This is true for all x. So the radius is infinite. Okay, that's meeting part 1. Meeting part 2 is finding sums by recognizing the functions that they represent. Okay, so example 3. Find this sum. Find the value of this series. The sum as n goes from 0 to infinity of the quantity minus 1 to the n, pi to the 2n, that quantity divided by the quantity 6 to the 2n, and the quantity 2n factorial. Okay, anybody have an idea how to proceed here? Kenzie?
Can we pull the pi to the 2n over 6 to the 2n to the side and have that be pi over 6 to the 2n as like an x?
Great. Now, why are you doing that?
Because the negative 1 to the n over 2n factorial is very similar. It ends up being very similar to this one right here.
Yeah, so what we want to do is we want to recognize the form So the form is cos of parentheses is the sum as n goes from 0 to infinity of minus 1 to the n, parentheses to the 2n over 2n factorial. So that's the form that's at work here. So what Kinsey is suggesting is we want to put our function, or put our sum into something that resembles that form a little bit better. So let's write this as the sum as n goes from 0 to infinity of minus 1 to the n over 2n factorial, and we just pull the pi and the 6 together. And so all we did here is we put our series into a form that matches that form. So put our series into a form that matches. So then what is this? Yeah. Exactly. Because cosine of parentheses is this thing. So this is cosine of pi over 6. Somebody else who hasn't answered today, what is that? What's cosine of pi over 6? Cosine of pi over 6. Annika? Square root of 3 over 2. So we found the value of the series by recognizing the function that it represented. Example 2. Example 4. Find the value of this. 1 minus ln of 2 plus ln of 2 squared over 2 factorial minus ln of 2 cubed over 3 factorial plus so forth. Let's give this a name. Let's call it S, sum. Sum equals that. Find the value of this sum. Okay, so we're going to do the same thing we did over here. We're going to have to recognize our form. Anybody recognize that form? Now notice our sum has ln in it, but it's not this. I mean, what we have is not powers of x divided by numbers. We have powers of ln2 and then divided by factorials. Yeah?
Is it the e to the x1, but x equals...
Right, so let's recognize the form. Now, Jason, it would be more useful to just talk about the empty version. The empty version of that, the empty version of e is e to the parentheses is 1 plus parentheses over 1 factorial plus parentheses squared over 2 factorial plus parentheses cubed over 3 factorial and so on. Does ours match that form, Jason? Yeah. Can anybody think of how how we can rewrite our series so it matches that form? notice that up there, e to the x, that's a power series, powers of x. Our series is not a power series. It's just a series. That's okay. So what can we do to our series to make it match that form? Our series is alternating. Is there any way to write our alternating series in a form that doesn't look like it's alternating? Kinsey?
Can we use x equals negative natural log of 2?
Right, so our sum equals 1 plus a minus ln of 2 plus a minus ln of 2 squared. That's going to kill the minus sign over 2 factorial. Plus a minus ln of 2 parentheses cubed. Oh, that minus sign is going to survive. And so forth. So that's going to accomplish the alternating, but written in a form that doesn't look like it's alternating. So what is this equal to? What is this? So it's the e to the parentheses series stuffed with a minus ln of 2. So this is e to the parentheses stuffed with a minus ln of 2. There we go. But that's not a number. That's a number, but that's not simplified. Can anybody think of how to simplify this? Raise your hand if you know this. What's e to the minus ln of 2? Alexandra, your hand is tentatively going up. No. I'm glad you said that because you're right in line with my previous class. Yeah. Well, look, how do you get there? Can you go one step at a time? Yeah, this is 1 over e to the ln of 2. So remember that a to the minus b means 1 over a to the b. It doesn't mean the negative of a to the b. And then this is 1/2. So there's our value. We found the value of our sum by recognizing that it represented e to something. So that's, again, this second part. Finding sums by recognizing the functions they represent.
Wow, for something so crazy, it can just be 1/2.
Right, yeah. And why would you want the crazy thing? Meeting part 3 is finding series by integrating known series. Okay, so example. Example 5. Remember I said that there are 6 examples today and the first 5 are easy. But the thing is, this is the cool one. So everybody wake up. Find the power series, or find the Maclaurin series for this. Okay. I'm going to give our series a name. I'm going to call it capital F of X. You'll see why. So this thing. Now, how do I do that? Well, we have a series, a form for e to the parentheses. So we're going to use the form for e to the parentheses. That's sitting right there. So this is going to be the integral of the sum as n goes from 0 to infinity of parentheses to the n over n factorial. Now what's inside those parentheses is minus x squared. And then this is all sitting inside of the integral symbol. Okay, well, let's clean this up a bit. This is the integral of the series n equals 0 to infinity. I'm going to have minus 1 to the n times x to the 2n over n factorial. Anybody remember how to do this? Well, there's a big theorem, remember, that says that we can bring the integral inside the summation. Because those are two processes. So here's a term. There are two things going on. One is do this, which is a limit of partial sums. And then there's another thing, which is this, which is a limit of its own. It's well, anyway, this is two limiting processes. And so I can bring the integral inside. But those things involving n don't involve x, so I can bring those out. So the sum as n goes from 0 to infinity of minus 1 to the n of x, and then the integral of x to the 2n, and on the bottom I have n factorial. All right, so what is that indefinite integral? Raise your hand if you know that one. Indefinite integral of x to the 2n. Ooh, Liam, I thought you were going to raise your hand. What is that? Power rule. How do we find Jason? Good. So this is going to be sum as n goes from 0 to infinity of minus 1 to the n over n factorial x to the 2n plus 1. Oh, and I should put this on the bottom. 2n plus 1 over here with the coefficients, and then we have x to the 2n plus 1. Oh, yeah. A little bit of history for you. Remember from Calc 1? Let's let f of x be e to the minus x squared. Anybody remember what famous function this is called? But a more common name, reflecting the shape of it? Bell curve, right. Okay, what about an antiderivative? What's the antiderivative? How do we do that? We use substitution. Substitution doesn't work. Integration by parts. No, integration by parts doesn't work. Dang. Nothing seems to work. Remember this from Calc 1? This antiderivative cannot be written as a normal function. That was a big bummer. What did we do in Calc 1, though? Later in the semester in Calc 1, we were able to come up with something which works as an antiderivative. It was this. So we build what's called an area function. Remember that if you take the derivative of this using the fundamental theorem of calculus, so the derivative of capital F, that would be the derivative of this crazy integral from t equals 0 to t equals x of e to the minus t squared dt. You use the fundamental theorem of calculus. It says just pull out the integrand and change the variable to x. So that capital F, this wacky thing, really is an antiderivative of that bell curve. Okay, so what we've just found is another way of writing the antiderivative as a power series. Another way of writing an antiderivative is this thing. Capital F of x equals the sum as n goes from 0 to infinity of minus 1 to the n x over n factorial to n plus 1 times x to the 2n plus 1 plus c. Hey, where's the plus c in this one? Why is there no plus c there? Well, it's because this is a particular antiderivative. If I put a different number there, I actually get a different antiderivative. All the different antiderivatives differ by a constant depending on what the starting value is for this integration. So this is one particular antiderivative. This is actually one particular antiderivative. The general antiderivative would have a plus c there. So it's a really cool, really rich problem. All right. So again, that was not the hardest problem, but it's maybe the most interesting because it's so rich and it makes you remember how much fun Calc 1 was. Okay, meeting part 4. Using series to find approximate values. All right, so I'm going to pose the problem that's going to be example 6, and then I'm going to go over to the sideboard and put some review stuff up. So example 6. Find an approximate value of this thing. Integral from 0 to 1 of x cos x cubed that is accurate to that is correct to 3 decimal places. Now, I'm going to make a name for this. I'm going to call this capital I for integral. So what we're really trying to find is find approximation such that, absolute value of I minus the approximation is less than 0.000001. If the difference between the approximation and the actual thing is less than that, that means the first 3 decimals in the approximation are going to be correct. Now, why do we need an approximation? Can't we just integrate this? Well, you can on helpmecheatonmycalculus.com, but this is not an integral that we know how to do. Well, maybe, do we know how to do this with integration by parts? I don't think so. So, we're sort of stuck here. I lied when I said I was going to pose the problem and then I was going to go over to the sideboard. I'm not going to go over to the sideboard just yet. Now I'm going to write headings down, but I'm going to skimp on some of the details. So the first thing I'm going to do is I'm going to get a Maclaurin series for cosine of x cubed. Well, from what we've done today, I think you can see where this would come from. Cos x cubed would be that I get that form for the cosine function. So I write the sum as n goes from 0 to infinity. I have 1 minus 1 to the n over 2n factorial. And then I put x cubed in the parentheses. And I raise that to the 2n power. So that's going to be the sum as n goes from 0 to infinity of minus 1 to the n x to the 6n over 2n factorial. And then I'm going to get Maclaurin series for x cosine of x cubed. So I'm just going to skip to the result, because again, you've seen enough of this. X cos x cubed, well, I can just park an x in front of that whole thing, but then it gets sucked inside. And I end up with sum as n goes from 0 to infinity of minus 1 to the n times x to the 6n plus 1, all divided by 2n factorial. I'm going to try to squeeze this in. Get Maclaurin series for this. The integral of x cos x cubed. Now remember how that works. That means I put all this stuff inside of an integration symbol. But that means I can then bring the integration symbol inside, and it ends up only acting on this. When you integrate x to the 6n plus 1, what do you get? Annika?
X to the 6n plus 2 over 6n plus 2.
Right. So I use the power rule. I raise the exponent by 1, and I divide by the new exponent. So So that's the heading, and the result is that this indefinite integral of x cos x cubed is going to be the sum as n goes from 0 to infinity of minus 1 to the n, 2n factorial, and then the new exponent is going to be 6n plus 2, so I'm going to have a 6n plus 2 on the bottom, and then I'm going to have x to the 6n plus 2. All right, so we're inching our way towards that. And then, so now we're going to write the definite integral. So the definite integral is going to be this thing. But that means that I have to take the indefinite integral, n equals 0 to infinity, minus 1 to the n, 2n quantity factorial, 6n plus 2, and x to the 6n plus 2. All of that I think of as a function, and I have to evaluate it from x equals 0 to x equals 1. Okay, well this is, you're going to get really tired of writing this series, but the good thing is you'll have it memorized. So I have minus 1 to the n over 2n factorial, 6n plus 2, and then I have 1 to the 6n plus 2. That's the series when I plug a 1 in, and then the same thing, all this stuff, and I have a 0 to the 6n plus 2. Now, trick question. What's 0 to any power? Almost. 0 to the first power is 0. 0 squared is 0. 0 to the 100th is 0. 0 to the minus 3, that's not defined. That's 1 over 0. What about 0 to the 0? 0 to 0 is 1. That's the weird one. You have to look out for that. Because normally if you have a series with a bunch of terms with 0 to the power, you can just say, well, they're all 0. But wait a second. If there's a 0 to the 0, that one doesn't go away. But notice, in this series, we never are going to have 0 to the 0. The lowest power we're going to have is 0 squared. And then we're going to have 0 to the 8th. And then we're going to have 0 to the 14th, and so forth. So this whole thing is 0. So all that survives is that series with the 1s. And that becomes, well, all those powers of 1 are just 1. So the sum, so I equals the sum as n goes from 0 to infinity of minus 1 to the n over 2n factorial, and then over 6n plus 2. And there's no other stuff. So notice, this is a power series, or a Maclaurin series, which is a power series. So it's a kind of power series. This baby is just a series. There are no powers of x. All right. Anybody notice anything about this series? It's alternating because that thing, this is going to be an alternating series. I don't even have to go to the sideboard. I can just go over here. So remember, so here's a blast from the past, from when we first started learning about series. So if we have a series, call it S, and it's going to be say A0 plus A1 plus all the way up to A to the K plus A to the K plus 1 plus, and goes on forever. I can break this up, and so this is AK plus 1, AK plus 2, and so forth. So there's an infinite tail that goes on. But I could think of this, what do you call this? If I just add up the first K of them. This is the kth partial sum. And we denote this by S subscript K. Oh, this, and then what do we call this? This is the remainder, RK. So we get S equals SK plus RK. Now, we had a question of what happens if we decide to approximate this by using this. So when we approximate S by saying that S is roughly equal to SK, we commit an error. So the error is the absolute value of the error is the absolute value of S minus SK, and that's the absolute value of RK. Now, anybody remember something about alternating series? Yeah, the alternating series estimation theorem. The alternating series estimation theorem. You know, figuring out what this error is hard because the error is a whole series of its own. It's an infinite tail. But for alternating series, anybody remember what this is? You know, this stands for the error that I commit when I only use SK instead of all of S. It turns out that all you have to do is look at the very next term. So you don't have to worry about the fact that this tail goes on forever. The error, RK, is less than or equal to that, less than or equal to that. So if we have some desired error, if we have some desired error bound, so error, the strategy is choose K big enough so AK is less than that error. So that's going to make sure that, oops, sorry. Maybe I should make a different symbol for this. The error bound, let's call it E, epsilon, E-P-S-I-L-O-N. We want this to be so if we choose AK to be smaller than epsilon, then our actual error which is RK That's going to be less than or equal to AK, which is going to be less than or equal to epsilon. That's our strategy. We want to figure out a K that's big enough so that this is true, and that's going to make sure that our actual error is within bounds. Okay, well, I have just 2 minutes, so I'm going to kind of fast forward through this as opposed to the whole rest of the hour. So let's make a table, K and AK and SK. So when K is 0, our A0 is going to be, if I go through all of that, I get 1/2. And remember, I erased the problem. Remember what our desired error bound was? So our actual error has to be less than that. Okay, well, that's too big. Okay, let's look at 1. A1 is going to be, if I go through all the steps, I get minus 1/16. That's too big. That's bigger than that error bound. Let's look at when K is 2. A2 is going to be, if I go through all the steps, 1/336, and that's roughly 0.003. That's too big. But when I look at the third term, or the K equals 3 term, A3 is going to be, if you go through all the steps, this is really cool. Everybody wake up. This is minus 1/6 factorial over 2 and 10. This is roughly minus 0.00007. That's small enough. So that means that if I just use these first 3 terms, that'll be enough. So let's figure out what SK would be. S0 would just be A0, that would be 1/2. S1 would be A0 plus A1, that would be 1/2 minus 1/16. S2 would be A0 plus A1 plus A2, that would mean 1/2 minus 1/16 plus 1/336, and that's about equal to 0.440. There it is. There's our answer. Now, let me quickly go to the sheet of mycalculus.com. Let's integrate. What was our integral? X cosine of x cubed from 0 to 1. Go. Let's see. This doesn't seem right. Let's do on Wolfram. Integral of x cosine of x cubed. Is it x cubed that we had in there? Aha! roughly 0.440408. Isn't that cool? So our first 3 digits are okay. We did all this work to figure out that. It's as hard as the problems get in this course. It's really rich. Thank you all. Oh, I have quizzes to hand out. Thanks, Gabriel.